We are going to be continuing our studies of circles by looking at lines and segments that are said to be tangent to the circle. And in this particular lesson, we're going to be looking at what do we mean when we say something is tangent to a circle. And we're also going to be looking at two theorems that will help us answer a few problems. First, what does it mean for a line or a segment to be tangent to a circle? And by that, we mean something very simple. Let's imagine that we have a circle. In this case, it's the green circle, circle C. And we have a segment XY that only touches the circle at exactly one point, point X. We give that segment a special name. We say that it is tangent to the circle simply because it only touches the circle at one point, that point being called the point of tangency. Now that we know what a tangent is, we can ask what is the relationship between a tangent and its circle. So let's assume that we have a line AB, and this line AB is tangent to circle C at point P. That means that the line AB will only touch the circle at point P. We can see that line AB is going to be perpendicular to the radius CP. In other words, the relationship between a tangent and a circle is that a tangent line or a tangent segment is going to be perpendicular to the radius of that circle. And the converse is also going to be true. Remember that the converse, if the conditional is in the form if P then Q, the converse just switches the P's and the Q's, if Q, then P. So the converse statement of the theorem reads, if line AB is perpendicular to the radius, then you know that line AB is tangent to the circle. In other words, if you know that you have a tangent line, you automatically know that that tangent line is perpendicular to the radius of the circle. Conversely, if you know that a line is perpendicular to a radius, then you also know that that line has to be a tangent line. Now let's take a look at an example where we need to apply that theorem. We're given a circle, circle P, and we're told that circle P has a tangent segment KJ at point J. If KJ is a tangent line, then according to the theorem that we looked at, KJ has to be perpendicular to the circle. KJ has to make a 90-degree angle with the radius JP. And if that's the case, then we have a very special type of triangle. We have a right triangle. And all right triangles need to follow the Pythagorean theorem. So assuming that KJ is tangent, it does make a 90-degree angle. Let's see if it follows the Pythagorean theorem. KJ is going to be 9, JP is going to be 6, and then KP is going to be the sum of 4 and 6. 9 squared is 81, 6 squared is 36, 10 squared is 100. On the left-hand side, if we add up 81 plus 36, we're going to get 117. And notice that's not the same as 100. Therefore, we have a false statement. So it cannot be the case that KJ is tangent to circle P because it doesn't follow the Pythagorean theorem. Therefore, KJ is not tangent to circle P. In the previous example, we saw a problem that dealt with lengths and using lengths to solve what was going on. Another common type of questions that you can come across are questions that involve angles. So in this particular one, we are told that line M is tangent to the circle at B, line N is also tangent to the circle at C, and we want to know what's the value of X. Because I know that B and C are point of tangencies, I know that the measures of angle ABT is 90 degrees. The other measure of ACT is also going to be 90 degrees, and I can already use that information to solve the problem. Because if you notice, ABTC is a quadrilateral. And for all quadrilaterals, if you add up all of the interior angles, you should always add up to 360 degrees. So that's the equation I have now. Replacing each angle with its corresponding value, I have x plus 90 plus 135 plus 90 equals 360. Combining like terms, I get x plus 315 gives me 360. subtract 315 from both sides, I find out that x is equal to 45 degrees. And this question is also interesting because we can begin to ask the question, what is the relationship between segment BA and segment CA? In other words, what is the relationship between two tangent lines that meet at a common point outside of the circle? So over here, I have another circle with two tangent segments, ZX and ZY. And again, I want to ask, what is the relationship between those two segments? The first thing that I notice is that the radii are going to be congruent to each other. If you have a circle, the radius is always going to be the same no matter where it is that you are on the circle. So Tx and Ty are both congruent to each other. Now imagine that you draw a segment from the center of the circle to point Z. According to the reflexive property, TZ is going to be congruent to itself. Now, you have now created two triangles. Those two triangles, by the hypotenuse leg theorem, are going to be congruent to each other. So the corresponding parts of the congruent triangles are also going to be congruent. We can say that ZY is going to be congruent to ZX. And all of that can be easily summarized in the following way. Let's assume that we have a circle with two tangent segments. In this case, it will be segment AB, segment AC, and they share a common exterior point. In other words, they're going to meet up at a point outside of the circle. If all of this is true, what we just saw says that AB has to be the same distance as AC. So if AB is 5 meters, AC is going to be 5 meters. If AB is 25 meters, AC is also going to be 25 meters. And with that, that's the end of the lesson.